Over the last century, many methods have been used to prepare amino acids in the lab. And in this video, we're going to take a look at a few of those methods. The first one is amino acid synthesis via an alpha halo acid. And this is one of the oldest methods for preparing racemic mixtures of alpha amino acids. It involves the use of the Hell-Volhard-Zielinski reaction that we saw in chapter 21, where we make an alpha bromo carboxylic acid. And then once we make our alpha bromo carboxylic acid, we can replace the halogen, our bromine, with an amino group in an SN2 reaction. So take a look here. This first part, this would be your Hell-Volhard-Zielinski reaction, where we take our carboxylic acid, we treat it with bromine and phosphorus tribromide. That makes the alpha bromo acid bromide. Then that gets hydrolyzed with water to give you this alpha bromo carboxylic acid. Now again, the reason we call this an alpha bromo is the carbonyl carbon, the carbon adjacent to it is the alpha carbon, so this is an alpha bromo carboxylic acid. Okay, so that's our Hell-Volhard-Zielinski reaction. And so we can do an SN2 reaction with that alpha bromo carboxylic acid using excess ammonia. And earlier on, we saw that polyalkylation is often unavoidable when ammonia is treated with an alkyl halide like you see here. However, in this specific case, polyalkylation is not a problem because the alkyl halide, so all of this, is relatively large and steric hindrance prevents subsequent alkylations. You also might remember from back in chapter 21 a neat reaction we looked at called the malonic ester synthesis, which is where we could prepare carboxylic acid starting with diethyl malonate. And a clever adaptation of this process is called the amido malonate synthesis. And what it does is it employs this reagent here, diethyl acetamido malonate, as the starting material, which enables the preparation of a racemic alpha amino acid. And so what we do is we take this starting material, our diethyl acetamido malonate, and we know that this is definitely the most acidic proton in the molecule. So when we treat that with sodium ethoxide, it deprotonates, and we end up with this carbanion. Then we can do an SN2, just a plain old SN2 on our alkyl halide. And the magic, so to speak, and these are my words, not the words of the author of the textbook, but the magic to me is in this step here, because when you treat this compound with aqueous acid, you hydrolyze both of these esters to carboxylic acids, and you might remember that it does a rearrangement and you end up losing CO2 in the process, and you produce the carboxylic acid that you have shown here. And of course, this is a racemic mixture. And so the process employs the exact same three steps in the malonic ester synthesis. Step 1 is going to be the deprotonation. Step 2 is our alkylation. And then step 3 is the hydrolysis. And I should have pointed out that not only does it hydrolyze the esters, but it also hydrolyzes this acetyl group here as well. And so since we're an acid, we end up with the amine being protonated. And again, we end up with a racemic mixture. And so keep in mind that the identity of the amino acid is going to be determined where? By the choice of the alkyl halide that we use. So let's say you wanted to make racemic phenylalanine. This is the structure of phenylalanine here. Well, this portion here, so maybe I should just circle this. Anyhow, this portion here is going to come from our alkyl halide. And so if we do a retrosynthesis, we would say we're going to need benzyl bromide or benzyl chloride or benzyl iodide. And you can see that they used benzyl bromide here. So in the first step, deprotonation. Second step, alkylation. And then the third step is the hydrolysis, and that would produce our racemic phenylalanine. So again, and I'm repeating myself here, but it is the structure of the alkyl halide that is going to dictate the identity of the amino acid that you synthesize. Racemic alpha amino acids can also be prepared from aldehydes using a two-step process called the Strecker synthesis. So the Strecker synthesis. And what we do here is we take an aldehyde and we convert it into an alpha aminonitrile using ammonium chloride and sodium cyanide. And then the second step involves the hydrolysis of the nitrile to a carboxyl group. So let's say we wanted to make alanine where we have a methyl group as our R group. In that case, we would want some aldehyde where we just have a methyl group. And so we would choose this aldehyde, which is acetaldehyde. Again, first step, treat it with ammonium chloride and sodium cyanide. That makes the alpha amino nitrile. And then you hydrolyze that alpha amino nitrile, or you hydrolyze the nitrile rather, with aqueous acid, and that gives you the carboxylic acid. And again, you end up with a racemic mixture. The mechanism of the formation of the alpha amino nitrile is shown here. And of course, we covered the hydrolysis of the nitrile to the carboxyl group in chapter 20. I'm not going to quiz you on this mechanism. I'll just leave it here as an FYI. Racemic mixtures of amino acids are produced from each of the three methods that you've seen so far in this video. But obtaining optically active amino acids requires either resolution of the racemic mixture or an enantioselective synthesis. Resolution is less efficient and more costly because half of the starting material goes in the garbage. It's just wasted. Resolution is not necessary if you perform an enantioselective synthesis. And this was covered back in chapter 8, even though I don't ask my students questions about it and I don't really cover it in detail. But Knowles developed a procedure for achieving asymmetric hydrogenation and then used that procedure for the enantioselective synthesis of L-DOPA. In this technique, the asymmetric hydrogenation employs a chiral catalyst and can be used to prepare amino acids with very high enantiomeric excess, or %EE. Many of the chiral catalysts that have been developed contain a ruthenium atom complex to a chiral ligand, such as BINAP. And you see an example of one of those catalysts shown here. It's pretty complex, but only small amounts of this chiral catalyst are required to prepare amino acids with very high enantioselectivity. For example, you can see here D-phenylalanine proceeds with a 99% enantiomeric excess when this chiral catalyst is used. Okay, in our textbook, this is question 25.12, not question 25.13, so we'll change it to 25.12. It says, identify the reagents that you would need to make each of the following amino acids using a Hell-Volhard-Zielinski reaction. And remember, the Hell-Volhard-Zielinski is just where we take our carboxylic acid, right? And then after the necessary steps, I'm kind of running out of space here, but anyhow, we end up installing the amine in this position here, and of course we make a racemic mixture. So if we wanted to make leucine, we would have to, we're installing an isobutyl group. So there's our isobutyl, there's our alpha carbon, so we have our carboxyl group like this. So this would be the starting material. And then the steps are, number one, we're going to treat that with bromine and phosphorus tribromide. That makes our alpha bromo acid bromide. Then we treat that with water to hydrolyze the acid bromide. At that point, it's not asking us for every detail, but at that point, what you would have would be this. Okay, you'd have the alpha bromo carboxylic acid. Then you would just treat that with excess ammonia to do your SN2. I'm kind of running out of space here, but anyhow. So there you go. That would give you racemic leucine. And if you wanted to make alanine, well, in that case, you would just need propionic acid because you just need the methyl group here. So this time I'm going to write out all three steps. So we'll put bromine in phosphorus tribromide followed by water. That would install our bromine at this position, right? That's what we'd have after those two steps. And then we would just treat that with excess ammonia. And that would give us our racemic alanine. So again, it's important to note that both products, both are racemic. Okay, we end up with racemic mixtures when we make an amino acid via or using the Hell-Volhard-Zielinski reaction. Okay, each of the following carboxylic acids was treated with bromine and phosphorus tribromide, followed by water. So this is step 1, this is step 2. Then you took the alpha halo acid, treated it with excess ammonia, so that's step 3. In each case, draw and name the amino acid that would be formed. So again, in this case, step 1, bromine and phosphorus tribromide, 2, water, and 3 is going to be some ammonia, like that. And what we would end up with in this case, hey, this looks familiar. We would end up with this amino acid, which is leucine. And of course, this would be racemic. And then for the second one, I'll just copy the procedure, paste it down in here. This one, we are going to have an isopropyl group, so we're going to make valine. So let's scribble that down. So there we go. And we end up with racemic valine. Okay, identify the reagents necessary to make each of the following amino acids via the amidomalonate synthesis. So if you just permit me to kind of scribble the diethylacetoamidomalonate here. Okay, so we have this diethylmalonate, and then we're going to have our acetamido group here, okay? And so this carbon is going to be the carboxyl carbon, and this carbon is going to be the alpha carbon. And so we need to add the rest of the molecule via our alkyl halide. So if we want to make isoleucine, which has a sec-butyl group, in that case, we're going to need 2-bromobutane would have to be our alkyl halide that we would use. So let me just outline the synthesis, and I don't want to run out of space here, but I'm going to rewrite the reagent down here. So here we go. It's a pretty ingenious synthesis, really. So there we go. So we're going to treat it step 1 with sodium ethoxide to do the deprotonation. Step 2, we're going to treat it with our alkyl halide, which in this case would be 2-bromobutane. And then step 3, we just hydrolyze the whole thing with aqueous acid, and we're going to heat that up, and that's going to give us our product, which is going to look something like this. Now keep in mind that the amine is going to be protonated because you're in strong acid. There we go. If you want to make alanine, again, and you probably noticed from the first example, these 2 carbons came from here, right? These 4 carbons came from here. So if we just want to add a methyl group, we're just going to need methyl iodide or methyl bromide or methyl chloride. So let's write that down, and repetition is the best way to remember this. So we're going to put our starting material, our acetoamidomalonate. So I'll try to draw a little bit neater this time. It's not working, is it? Anyhow, so, there we go. Step 1, our sodium ethoxide. Step 2, we'll put our methyl group for our alanine. And step 3, we're going to cook that up with some acid, and that's going to give us our alanine. And there you go, there's our alanine. And for the last one, for valine, we need an isopropyl group, so we're going to use isopropyl bromide iodide. Doesn't matter. So what I'll do for this one is I'm just going to actually copy and paste from the top one, just to make it a little bit faster. So I'll paste that down here. And you see that to make valine, all we have to do is modify the alkyl halide. So we'll just change that to an isopropyl. So now we're using isopropyl bromide. Maybe we can just move that over here like this. And then we just have to delete this methyl group. And so there you go. There's our valine. So we have our isoleucine, alanine, and valine. And keep in mind that all of these are going to be racemic. Okay, 25.15, an amidomalonate synthesis was performed using each of the following alkyl halides. In each case, draw and name the amino acid that you would make. So remember that when you do the amidomalonate synthesis, your alkyl halide, your R group that comes from your alkyl halide, after your chemistry is all done, is going to be, so I'll just write this part in red, okay? That's going to be this part here. So if we use methyl chloride, in that case, we're going to get alanine, right? Just like we saw in the previous one, I think we used methyl bromide. Okay, so for this one, I'm going to spell the whole thing out. So we have our starting material, acetoamidomalonate, And in the first step, we're going to treat it with sodium ethoxide. Step 2, methyl chloride. Step 3, we're going to hydrolyze it with aqueous acid. And so what we're going to get is going to be this NH3 plus, and that's what we have, right? So the methyl group comes from here. So if we go over the next ones a little bit faster, so now if we use isopropyl chloride, so if we used isopropyl chloride, right, then we're going to put an isopropyl group in. So we would have an isopropyl group like this, okay, and so we would end up with valine. So in the first one we made alanine, the second one we made valine, all right, and in the next one we're using 2-methyl 1-chloropropane. So if we right here, so 2-methyl 1-chloropropane, right? That's isobutyl chloride is essentially what this is. Not essentially, it is what it is. It's just a common name. Well, in that case, we're going to end up with an isobutyl group, and so we're going to end up making leucine is what we would end up with in that case. So we'll draw the product, which looks like this. And there you go. And that would be leucine in the sky with diamonds. All right, there we go. Okay, next we're trying to do a Strecker synthesis. So identify the reagents that you would need to make each of the following amino acids via a Strecker synthesis. So remember that when you make the alpha amino nitrile, that the nitrile gets converted into the carboxyl group. And so everything that comes before the carboxyl group has to come from your aldehyde. And so if we're trying to make methionine, so if I just draw the structure of methionine like this, oops, that's not the structure of methionine. Here we go. All right, and we're hydrolyzing an aqueous acid, so I'll draw the protonated form like this. So again, this carbon is going to come from your sodium cyanide, okay? But all the rest of it, all of this part here, that comes from your aldehyde, okay? So your aldehyde needs to have, if you count here, after the sulfur, 1, 2, 3 carbons like that. So we're going to start out with this aldehyde, so 1, 2, 3, the third carbon, right? If we go 1, 2, 3, like that, the third carbon is the one with the carbonyl. And so the steps are, number 1, ammonium chloride and sodium cyanide, and then aqueous acid. Step 2 is aqueous acid. That's going to hydrolyze to give you your methionine. Okay, now if we want to make histidine, again, I think it's easier to just start by drawing the amino acids first here. So let's draw histidine. It always takes me a second to dream up the structure of histidine. Okay, so we have a nitrogen here. Oops, didn't close my ring right. There we go, that's better. Something that looks like that. Okay, so there you go. There's my histidine, okay? And so again, this carbon comes from the sodium cyanide. So that means our aldehyde has to have these 2 carbons coming off of the ring. And so let's draw, we have 1, 2 carbons. There's our aldehyde, and so now we just need to draw that. This is called an imidazole ring. So it should look like that. There we go. So step 1 is going to be our ammonium chloride and sodium cyanide. And step 2 is going to be aqueous acid. Just like that. And the last one, phenylalanine. I'm going to go a little faster on this one with the phenylalanine. So with phenylalanine, you're just going to need, this would have to be, right, there's your methyl group. Yeah, so there's your carbonyl, like this. Not my neatest drawing. I'll try to make it a little more angular there. There we go. So that's our starting aldehyde. We need ammonium chloride, sodium cyanide, and aqueous acid. And that's going to give us our phenylalanine. I'll just abbreviate the aromatic ring as pH, just to simplify my life, which is complicated enough. All right, so again, the carboxyl carbon came from the cyanide, okay, and these two carbons and the aromatic ring, of course, came from all of this, okay, from your aldehyde. All right, each of the following aldehydes was converted into an alpha aminonitrile by hydrolysis to yield an amino acid. In each case, draw and name the amino acid that was produced. I've kind of done these already to some degree, but anyhow, if we started with acetaldehyde, okay, first step, ammonium chloride, sodium cyanide. Step 2, aqueous acid. Right, now we've got 2 carbons, so 1, 2. Then we've got our carboxyl, and remember our carboxyl carbon comes from the cyanide. And so in this case, we ended up with alanine. Let's see, alanine. There we go, that's better. All right, next one, if we have 3-methylbutanol, so 3-methylbutanol is going to look like this. So 1, 2, 3-methylbutanol. Okay, same old thing, ammonium chloride, sodium cyanide, followed by aqueous acid. And in that case, we're going to end up with leucine. So here we go. All right, and I know I've said this a lot in this video, but this carbon comes from the cyanide, right? And then all of these carbons come from the aldehyde. If you find it easier to kind of connect the dots that way, it might be useful for you. The next one is 3-methylpropanol. So if we have 3-methylpropanol, I don't want a highlighter. There we go. 3-methylpropanol would be this. So you can clearly see that we're going to end up with valine here. So step 1, getting mixed up here. Ammonium chloride, sodium cyanide, followed by aqueous acid. And that would give you, oops, not my best artwork. Come on, there we go. That would give us valine. All right. So this is valine, and I didn't write the name of leucine in, did I? So let's scribble it in here, leucine. All right, so alanine, leucine, and valine, respectively. All right, identify the starting alkene necessary to make each of the following amino acids via asymmetric catalytic hydrogenation. Let me just show you what the expectations are here. So if we want to make alanine, okay, keep in mind that this asymmetric hydrogenation always makes the L compound. All right, so we want to make L-alanine. So there's our chirality. And what you're expected to do is put the double bond here, okay? Then you want to put your acetyl group on here, and there you go. That's all you need to do. And then you're going to do your asymmetric hydrogenation. Okay, if we wanted to make L-valine, so again, we have an isopropyl group for valine. So I'll write this down here. So this would be L-valine, okay? Same thing, we have our double bond, we have our NH acetyl. There we go, except we need our 2 alkyl groups or 2 methyl groups like this, okay? And then if we wanted to make leucine, or L-leucine rather, okay, so the structure of L-leucine, it's gonna look like this. So there's our L-leucine. In this case, so there's our double bond, there's our acetyl group. All right, and so here we go, and we're going to do our asymmetric hydrogenation. And don't stress about the conditions, just know what the alkene would look like and that the amine is going to be protected as an acetyl group.